Well, hello and welcome back to another episode. It's great to see you all. I hope you're doing well. So today I want to continue with our series on building a linear algebra library in C++, and in this video in particular I want to focus on solving systems of linear equations. So we spent quite a lot of time up to now getting the basic infrastructure out of the way in terms of our code and our classes for handling matrices and vectors, and now we can start to have a look at some things a little bit more interesting and certainly a bit more practical. So really that's what I want to do today. Now I want to keep the introduction fairly short, so I'm not going to say too much now, except to say, as I always do, that if you like this video, please do remember to hit that like button, and if you haven't done so already, please consider subscribing to my channel and clicking on the bell icon so you get the notifications so that you don't have to miss any future videos. I do try to make a video roughly once a week, so if you subscribe, you don't need to worry about missing anything. Thank you very much. Right, well, without much further ado, let's jump to the computer and let's have a look how we can go about solving systems of linear equations in C++. Okay, so here we are. This is part 6 now of our series on linear algebra in C++, and as I just said, we're going to talk about solving a system of linear equations. Now, as we talked about in the previous video when I came to looking at computing the matrix inverse, I talked then about how we can go about solving systems of linear equations by computing the inverse of the matrix. So this is just a quick recap of what we looked at before. We started with a system of equations, something like this. So we have here 3 equations in 3 unknowns. So the unknowns x1, x2, and x3. And we have the coefficients a11 through to a33 and b1 to b3. And of course, we can write that in matrix notation as follows. We separate out the coefficients there, and we have the unknowns in a column vector there, and the b terms in a column vector there, like so. And then, of course, we can see that we could write that in the form of a times x equals b, where x is this column vector, a is this matrix, b is this column vector. And then we can see through simple algebra that if we wanted to work out the values of x, we can divide through by the matrix A. So we end up with a times 1 over a times x is equal to 1 over a times b, which, of course, is the same as saying x is equal to a to the minus 1 of b. And where a to the minus 1 is, of course, the inverse of this matrix. And that would indeed give us the solution to the system of linear equations, although that is not the best way generally to go about solving a system of linear equations, because it is not the most efficient way of doing it. So the other way of doing it is called Gaussian elimination. Now, I went over this and I gave a much more detailed overview of how Gaussian elimination works in the previous video. I'll put a link to that, of course, in the description below. But just to very quickly recap, our aim with Gaussian elimination is to transform the matrix A, the coefficient matrix, into what's called row echelon form, or sometimes called the upper triangular matrix. And once it's in row echelon form, it will look something like this. So we will have the lower left of the matrix is going to contain all terms of which are just 0. Okay, and then the top right of the matrix contains terms that are non-zero, or potentially could equal 0 as well, of course, and may or may not have the leading diagonal elements here equal to 1. In this example, I've put these as all equal to 1. That's not strictly necessary, and indeed for using Gaussian elimination for the purposes of solving a system of linear equations, we don't need to worry about making the leading diagonal elements equal to 1. So our objective really is just to make sure that all of the elements here at the lower left are equal to 0. Now, how do we do that? We are going to do that using elementary row operations, and these consist of adding a multiple of one row to another, multiplying a row by a non-zero number, and swapping one row with another one. And as I say, in the previous video I gave a much more detailed example of how we might actually go through that process. But we can consider a simple example of this system of linear equations here. Note now that I'm using x, y, and z for the unknowns instead of x1, x2, and x3, but otherwise it's really the same. Of course, we can write that out in matrix notation as we've seen in the previous example, and if we augment the far left part with the right-hand side, we get something like this, and then we apply the elementary row operations that we've talked about to convert that augmented matrix into row echelon form, and if we do that, we will get a result that looks something like this. So you see now the lower left corner elements here are all 0, and then the top right corner and the diagonal elements are non-zero. Okay. So we can then separate that back out into the terms of our original equation with our unknown, and we can see immediately from this we're going to have 6.111z is equal to minus 36.666 or 6.36.6 recurring. So quite obviously z is going to be equal to minus 6. I'm allowing there for rounding errors and the limited precision to which I've displayed these numbers. Now what we do from here is a process called back substitution. So now we know what the value of z is. We can then now go on to work out the value of y, because we know that 1 times y plus 0.5 recurring times z is equal to minus 2.333. So we can actually work that out. So this is the equation that we have therefore y is equal to minus 2.3 recurring plus 0.5 recurring times 6, or y is equal to 1. And we can do exactly the same. Now we know z and y. We can now work out the value of x, which gives a value of 4. Okay, so that is the process known as back substitution, and it really forms the core of what we're actually going to implement today. So in terms of our C++ implementation, we see that there are really two functions that we need to implement. We need a function that will convert a matrix into row echelon form using Gaussian elimination. Now note that this is slightly different to the inverting the inverse function that we created before. So we've already implemented Gauss-Jordan elimination for the purposes of calculating the inverse of a matrix. And this will have to be a separate function because we only want to do Gaussian elimination. We're not going to take it as far as we need to do the full Gauss-Jordan elimination for computing the matrix inverse. And indeed, that is the whole point of creating a specific function to do this, because it requires fewer computational steps than calculating the matrix inverse, and therefore that makes the whole process a more efficient way of solving a system of linear equations compared to calculating the matrix inverse and using that. The other function that we need to write is one that performs back substitution to solve for the actual values. So I've gone ahead and created a flowchart here for the process of Gaussian elimination. This may look a little bit complicated. I find it a bit difficult sometimes to fit these flowcharts in properly into the aspect ratio for video, for making nice videos. But it's not perhaps as complicated as it looks. And I think if anything here doesn't really make sense, it'll make a lot more sense when we come to look at the code in a moment. But the point is we start here. And the first thing we're going to do is check that the number of columns is greater than or equal to the number of rows. If it isn't, then we can't do Gaussian elimination, so we stop. Notice we don't require the matrix actually to be square, and that's because we're allowing for the fact that the user may have augmented a column vector onto the matrix in order to make the process work, as we've just seen. So if that condition is met, then we come down to here, we set diagonal index to 0, and we start a loop. So while diagonal index is less than number of rows, we come down to here, we set C row and C column both equal to diagonal index. Come to here, we set row index is equal to C row plus 1, okay, so the current row plus 1. While row index is less than the number of rows, so this is another loop, we then set row 1 value is equal to the value of the matrix at C col, comma C col. If that value is not equal to 0, we calculate the element value, which is simply the value of the matrix at row index, comma C col, and then we compute a correction factor equal to minus C element value divided by row 1 value that we've just got from here, and then we simply take the row indicated by row index, and to every element in that row we add to it the result of row 1 index of this value, the value of the matrix at row 1 index, comma whatever element in the column we're looking at, multiplied by the correction factor. So the point is this will work through the elements in the column below the current diagonal element, and we'll calculate the correction factor that we need to add to that element in order to make it equal to 0 based on a multiple of one of the other rows. Okay? And then simply we come back round, increment row index, come back to here, and we loop through there until we reach this condition where row index is no longer less than the number of rows, which means we finish, so we come back to here, and then we'll continue looping over the diagonal until that's finished. Once that's finished, we perform a simple check to see if the matrix is in row echelon form. If it is, then we know we need to stop. If it isn't, then we simply set diagonal index back to 0, and we repeat the whole process again. Now, I did explain this in quite a lot more detail again in the previous video talking about matrix inverses, so you can go and have a look at that. And also, I think when we come to actually look at the code shortly, anything that's not clear here will make quite a lot more sense. Okay, so The other function that we need to implement is the one that actually performs back substitution. So just to talk about how that's actually going to work, we've already seen this example here. This is the same example that we had before, and this is in the form of A times the vector x is equal to a vector b, where A is in row echelon form. And we could write that out in this form here, A00 to A22, and x0, x1 and x2, and b0, b1 and b2. Note that I've shifted to 0 indexing here simply to make it more relatable to the C++ code later on. So considering everything in that notation, the first result that we have comes from saying that 6.1 recurring times x2 is equal to minus 36.6 recurring, which is this. So we can see that x2 is equal to minus 36.6 recurring divided by 6.1 recurring, which is equal to minus 6, or, to put that algebraically, x2 is equal to b2 divided by a22. If we look back, this is b2 divided by a22, okay? Minus 36.6 recurring divided by 6.1. You can see where those have come from. Okay, right. And what about x1? Okay, so in the case of x1, we now have that 1 times x1 plus 0.5 recurring times x2 is equal to minus 2.3 recurring, okay? Or, in other words, x1 is equal to minus 2.3 recurring minus 0.5 recurring times x2, all divided by 1. And we can write that algebraically. That is actually b1, which is this number here, b1 there, minus a12, which is this number, multiplied by x2, all divided by a11, which is that number there. Okay, so we can see how we can calculate x1. And we do exactly the same process now for x0. So from here we have that 1 times x0 plus 3 times x1 plus minus 1 times x2, I've put the extra plus in there just for clarity, is equal to 13. Now, of course, we already know the values of x2 and x1, so we can plug those in, and we get that x0 is equal to 13 minus 3 times x1 plus minus 1 times x0, all divided by 1. That's a mistake, isn't it? That shouldn't be x0 there, my apologies. That should be, of course, x2. It should be 3x1 plus minus 1 times x2. Or, to put that algebraically, what we actually have is x0 is equal to b0, that's 13, minus a01, which is 3, times x1, which is there, plus a02, which is minus 1, multiplied by x2, which is there, all divided by a00, which is there. So if we have a look at those, we have, that's the formula for x2 is simply b2 over a22. x1 is b1 minus a12 x2 all over a11, and x0 is b0 minus a01 x1 plus a02 x2 all divided by a00. So how can we actually put that together into one form? Well, it turns out we can actually write that in this form here. Okay, so this simple equation simply means that we take x of n is equal to b of n minus the sum over n is equal to n plus 1 to big N minus 1. So big N is the number of unknowns, okay? N is, of course, this variable here, multiplied by ANM times XM all over ANN. And if you work that out, you can see that, go through it on paper if you want to, pause the video and have a look at that if you like, you can see that that will equate to the same thing. So if we have x of 2, so n equals 2, we get b2 minus, now this is going to be then be the sum from m equals 3 to n minus 1, so big N is of course 3, so that's going to be 2. So the sum from 3 to 2 doesn't make any sense, so that would not evaluate. So we end up with bn minus 0 divided by a22. And you can see that is exactly the same as the equation that we have here. Similarly, if n is equal to 1, so we have x of 1, we have b1 minus, now this is then going to be the sum of m equals n plus 1, which is 2, to n minus 1, which is 2. Sum from 2 to 2 is evaluable. Okay, we're going to get just one term, which is then going to be a 1 comma 2 times x of 2 divided by a 1, 1, which is exactly the term that we have here. And you can see again, if you were to plug in x equals 0, then that's going to give the same thing. Now, this isn't strictly the correct notation for this, because I'm just assuming that it's obvious this sum doesn't evaluate when the bottom term of the sum is greater than the top term, and that's not strictly how you would write things normally. But in terms of code, that is how we're going to do it. And of course, also strictly speaking, this is iterative. It assumes that so each next value of x of n relies on you having computed the previous one. So this could have been written as x of n plus 1 and so on. But I think this notation is actually clear enough. So you have to start from x2, and then you can work out x1 and then x0, or indeed for however many elements of that you may have. So, and finally, just to make that more clear, this is the actual notation that we have here. So after Gaussian elimination, our A matrix looks like this. And you can just see, you can quite clearly see how that's all working. The terms here are coloured similarly like so. If we put that together into a flowchart, we get something like this. So this is the basic flowchart for the function for back substitution. We're going to accept as index A matrix and B vector, so the A matrix and the column vector for B. We join those together, we convert that to row echelon form, and then we set current row is equal to num rows minus 1. And then we loop while current row is greater than or equal to 0. If it's not, we end. If it is, then we come down to here. We do current column is equal to current row plus 1, and then we set CR is equal to the value of the matrix at current row, num cols minus 1. So that's going to take the B value, okay? And then we set test if current col is less than the number of rows. If it is, we set A is equal to the value of the matrix at current row, current column. B is equal to the output at current column, so that's the previous value at current column. And cumulative sum then plus equals A times B, and then we increment current column and we loop until we have finished looping through that column, and then we come back down to here, and then we compute the output at current row, which is simply equal to CR minus cumulative sum divided by the value of the matrix at current row, and then we decrement current row and come back round to here. As with the previous flowchart, I think once we come to really look at the code for this, that's really all going to be a lot more clear. So I think that's really what we should do now. We should move on and have a look at the code. Okay, so the way I've approached writing the code for this is that I've made some modifications to the qbmatrix2 class that we've been working on and building up so far. So within that, I've created the functions to actually implement the Gaussian elimination process, and also a function that allows us to tell whether the matrix is in Gaussian, is in row echelon form or not. And I've then gone about creating a new function called qblindsolve that actually runs through the whole process of solving a system of linear equations. Now, I decided to do it that way because I wanted the user to have a simple function that they could call, and they simply have to pass it the A matrix and the B column vector. It will tell them the values of their unknowns. And I just thought that was really quite a nice, neat and tidy way of doing things, so that's what I've done. Anyway, I'm going to go through the code now, so let's go and have a look at it. Here we are. We're in the qbmatrix class, so that we've been working on all along so far. And as I say, what I've really just done is added two new functions to this. I've added one function here, simply called row echelon. It returns a matrix in the form of qbmatrix2, of course, of type T, and simply called row echelon, right? And the purpose of that is to convert the matrix into the row echelon form. So it will simply return the row echelon form of whatever matrix that we call it from. And the other function that I've added that I want to talk about today is simply here. This function here is row echelon. One minor thing to talk about, I've taken the two functions here, is square, and the new function is row echelon, and I've taken them out of the private functions and I've put them into the public block because I found actually it's quite useful to have access to these. Now, anyone watching this that's really paying attention is going to see that there's also a new function here called rank, and the purpose of that is to compute the rank of a matrix. Now, we're not going to talk about that today. That will be the subject for the next video, so you've got that to look forward to. Anyway, so today, first thing, I want to talk about this function here that simply will identify whether a given matrix is in row echelon form or not, and it returns a Boolean true or false. Depending on whether the matrix is in row echelon form. So let's have a look at that first. So here we go. So this is our function to test whether the matrix is already in row echelon form. And of course we start this as we do before. It's not very long, it's only this code here. We declare a template class T as before because we don't know what type of variable the user will be using for their matrix. And we have our boolean. It's a member of the QB matrix 2 class of type T, and of course the function name is row echelon. So the first thing, what we're actually going to do is we're going to test that the sum of all of the elements in the lower triangular matrix is equal to 0. So we're going to basically just run a cumulative sum over all of the elements in the lower triangular matrix, as we saw just now in the slides, and make sure that the result of that sum is equal to 0. Obviously, if the matrix is already in row echelon form, then the result of that sum should be 0. Otherwise, clearly, we're not in row echelon form. So initially, we initialize a variable cumulative sum. We set it to 0. Of course, I'm static casting to type T because we don't know what that is at this time. It could be anything. And then we simply loop over all of the rows. So we have a simple loop here for I equals 1 to m underscore n rows. And then within that, we're going to loop over all of the columns that correspond to the lower triangular matrix. Notice that we start I from 1. Okay. Now, the reason we do that is when the matrix is in row echelon form, the first row, we don't need to consider that. It doesn't have to have any zeros in the first row. In fact, the first 0, for it to be in row echelon form, the first element that absolutely has to be 0 is the first element of the second row. So we start with I equals 1, which of course gives us the second row. And then we're going to loop over the columns from 0 to I. So for the first time through this loop, I will be 1 because we're looking at the second row. Okay, remember this is 0 indexing because we're using C++. And so J is going to loop from 0 to less than 1. So we'll only look at one element, which of course will be the first element. And then we'd simply do cumulative sum plus equals the value of the matrix at the location ij, which we convert to a linear index using the sub2in function that we've talked about in the previous videos. And that's it. And then we're going to loop over all of the elements in the column and then drop out of that loop and then loop over all of the rows. And you can see pretty simply how that's going to work. And then we simply test whether the result of that cumulative sum is close enough to 0. Now, the reason we use close enough is because if we're using double precision floating points, we can be really, really close to 0 without necessarily being equal to it. And in fact, it's actually okay to accept a certain degree of tolerance. Again, we talked about that in the previous video where we looked at calculating the matrix inverse. So we don't simply test if cumulative sum is exactly equal to 0. We use this close enough function that simply tests if it's within a specified tolerance of 0 that we're prepared to accept. Okay, and that's it. That is a simple function that will return a boolean to indicate whether our matrix is in row echelon form or not. So let's now have a look at the function that actually converts the matrix into row echelon form. Okay, so here we go. This is our function that we're going to use Gaussian elimination to convert the matrix into row echelon form. Okay, so we have our function declaration, we don't accept any input parameters, and we're going to return a variable of type QB matrix 2 of type T. Okay, so we test first that the current matrix must have at least as many columns as rows, but note that we don't actually require it to be square, since we're going to assume that the user may have combined a square matrix with a vector. They would do this, for example, if they are trying to solve a system of linear equations. So at the moment, we're in the QB matrix 2 class, and we're really just talking about these are generic functions. We might generically want to calculate the row echelon form of a matrix using Gaussian elimination for some other purpose. We might not be trying to solve a system of linear equations, so it makes a lot of sense, I think, to keep that general. Okay, if the number of columns is less than the number of rows, then we throw an exception, simply saying that the matrix must have at least as many columns as rows. Otherwise, we can come down here and we can start the main part of the process. So we are following the process that we saw in the flowchart just now. So we've first of all initialized C row and C col. We set max count to 100. This is going to be the maximum number of iterations we'll allow the process to run through. If we recall from the flowchart, if it doesn't succeed the first time, it goes around and we'll have a go at running through the process again. So obviously we want to impose a limit on how many times that's allowed to happen. Otherwise it could potentially just run forever, which would be really annoying. We set count to 0. Obviously we're going to use that to count how many times we've been through the process, and we set our boolean flag here, complete flag, equal to false, because of course we haven't finished yet. And then we set up a while loop, so while not complete flag, so while complete flag is false and count is less than max count, we're going to do everything in here. Now the first thing that we do is we loop diagonal index from 0 up to the number of rows, so that will loop over all of the diagonals of the part of the matrix that corresponds to the A matrix. Okay, so if the user has augmented a column vector onto the end, that will not be counted here. So, okay, because that doesn't affect the number of rows, it only affects the number of columns. Okay, so as we saw in the flowchart, we set C row equal to diagonal index, and we set C column equal to diagonal index. And what we're going to do now is simply consider the column. Now, those of you that have been paying attention to my previous videos will see that this is essentially the same code that we used to perform part of the Gauss-Jordan elimination process, and it is. Really all that we've done is taken out the partial pivoting where we swapped rows around. We don't need to do that here, and we're not considering the rows, and we're not trying to set the leading diagonal elements to 1. So all we're going to do is loop over the diagonal elements and ensure that all of the elements in the column below that diagonal element are equal to 0 or close enough to 0. Okay, so we loop from row index is equal to C row. Remember, C row is diagonal index plus 1. Okay, so that's going to be the next row down from the element that we're looking at, while row index is less than the number of rows. And then we might as well check if this element is already equal to 0, then we don't need to do anything. Obviously, there's no point doing anything, so we use our close enough function to compare the element of the matrix at row index C col with 0. If it's not close enough, then we're going to do stuff. Otherwise, we can just ignore it and move on. Okay, so we need to obtain the element that we work with from the matrix diagonal. Okay, so as we aim to set all the diagonal elements to 1, this should always be valid for a matrix that can be inverted. Now, in fact, this has, that's very interesting. This comment here has come because I've copied and pasted the code from the previous example. It's very interesting to note we don't actually need to do that. The first thing that we're going to do is set row 1 index equal to C col, okay? And then we extract the current element value stored there. So we get the value stored at the current element. So we're going to extract current element value is equal to the value of the matrix at row index, comma C col, okay? We're then going to get the value stored at row 1 index C col. Now row 1 index is equal to C col, so that's essentially C col, C col. Okay, so row 1 value is equal to that. That's the diagonal, effectively, okay, because C col is equal to the diagonal index. So that will give us the diagonal, essentially. And we're going to see if that value is close to 0, then just move on. Okay, so row 1 value, if row 1 value is close to 0, then we can't do anything because we're going to divide by this value. So if it's close to 0, then it doesn't make any sense to do that division. So we just ignore that and move on. And we hope that when we come through the process again, that that problem will be solved. Okay, and if it's not close enough to 0, if it's not close to or equal to 0, we set our correction factor as simply equal to the current element value divided by row 1 value, and then we use the mult add function that we talked about in the previous video to add a multiple of one row to another row. Okay, so it takes the correction factor, multiplies the row at row 1 index by that, and then adds that to row index. Okay. And then that's it. We finish all of those loops, okay, so we drop out of the final for loop there. And now we need to see, have we actually achieved the result that we want? So we just do complete flag is equal to this dot row is row echelon. So we simply use the function that we talked about just now to test whether the matrix is in row echelon form. If it is, then of course complete flag is going to be true, otherwise complete flag will be false. And then we just increment our counter, and then we end the while loop. And we see that this will drop out if complete flag has been set to true, or indeed if the count exceeds max count. Okay, and that's it. And then we simply form the output matrix. We create a new instance of the qbmatrix2 class called output matrix of size m_n rows, m_n cols containing the matrix data, and we return output matrix. And that's it. So an interesting point to note, actually something I don't like about the way that I've written that, is that at the moment this will actually modify M matrix data, so it will modify the matrix that we're talking about, and actually that isn't strictly what we want to do. The way around that would be to add code to simply make a copy of m_matrix data before we start the process, and then work with that. So yeah, that's interesting. I didn't think that. Okay, so in a sense, really, we don't need to have a return value because it's actually going to convert the matrix that we're working on into the row echelon form. But that's, for now, that will do. This is how I've written it. It does actually generate a return form, and it will modify the form of the original matrix. That's interesting. That is a little bit untidy. I'm not too keen on that, but never mind. So the row echelon function effectively works in place. It converts the given matrix into the row echelon form. Okay, right, that's fine. Okay, so that's actually really it in terms of the changes to the qbmatrix2 class. Okay, so the only other thing that I've done is to create the qblinsolve function that is actually going to be, allows the user to actually perform the to calculate the solution to a system of linear equations. So let's have a look at that now. So if we look at, here we go, qblinsolve.h now, because I'm using templates, I'm writing everything directly into the header files. This is not my favorite way of doing things, but as I understand it, it is the right way to go about it because we're using templates, so we're doing that. So we have a function here called qblinsolve. So of course we hash include a bunch of stuff. We bring in qbmatrix.h and of course qbvector.h. Note the unusual path here. I've mentioned this before, simply because of the way I organize my videos. I have these files in different locations. Because we are building a C++ library, ultimately we want to bring those together into one folder. But for now, I have them in separate folders, so I have to put the path there. You may well have a different path if you've been following through writing your own code, so do just bear that in mind. We then define our function qblinsolve. It's going to return a qbvector, a variable of type qbvector, which of course will hopefully contain the solution to our system of linear equations, and it accepts as input a const qbmatrix2 matrix here of type t called a matrix. We bring in actually a pointer to that, and we bring in a pointer to a qbvector object also of type t and also declared const. And this is obviously going to be the B column vector that we talked about before. So the first thing we're going to do is make a copy of the input matrix called A matrix. So that, in a sense, will take care of the problem I just talked about with my implementation in qbmatrix, where computing the row echelon form will actually modify the matrix that you're dealing with. Because we make a copy first, we don't need to worry about that. And indeed, because we've declared const here, we're telling the compiler that anything that makes a change to A matrix is obviously wrong. So we make a copy of that. We simply set input matrix is equal to the dereferenced form of the A matrix. And then we're going to combine the input matrix and the B vector together into a single matrix ready for using the Gaussian elimination to reduce it to row echelon form. So the first thing we do is extract the data from B vector, which is a QB vector. And what I want to do is extract that into an instance of std vector or stud vector from the standard library. So we extract the number of dimensions, which is bvector.getNumDims. We then set up a instance of std vector of type t called bvectData, and then we simply loop over the dims, over the numdims, and we push back into bvectData the value of bvector at I. Okay, so that's pretty straightforward. So we're copying all of that. Now, once we've done that, we actually want to convert that into a qbmatrix2 form. So the whole reason we have to do this is because we need a qbmatrix form of our data, essentially a column vector, which we can represent using the qbmatrix2 class. We talked about in the previous video on vectors why it makes sense, though, to have a specific class to handle vectors. Okay, so we define our qbmatrix2 instance here of type t called b matrix of size numdims by 1, and we pass to that the reference to the bvect data that we've just created. So that will initialize b matrix to essentially be a column vector with the same data as was passed by the user here. And then we join those two together. We do input matrix.join b matrix. We talked about the join function before in the previous video. So that will give us the augmented matrix that now contains all of the terms of the A matrix and the B vector augmented together. And now, of course, we use Gaussian elimination to convert that into row echelon form. So we simply create a new matrix called row echelon matrix, which is equal to input matrix.row echelon. And as we've just discussed, actually calling the row echelon function can change input matrix into the row echelon form as well. So that is slightly redundant, but Never mind, I think we can live with that. It's something I will come back to and tidy up at a later time. Actually, that's really the kind of thing that's often picked up during code refactoring, which really goes on to highlight precisely why code refactoring is very useful and can be quite important. And indeed, you see, I didn't spot that until I came to talk through this code to, and talk about the code to you. I hadn't spotted that that problem was there. So it just goes to show how useful talking through your code can be. Okay, we're then going to create a qbvector object to store the output, which initially we're going to populate with the data from bvect data, but of course we're going to modify that with the elements as we compute them. We populate it with that data just so that it's initialized to the right side. Okay, and now we're going to use back substitution to actually compute the result. Now this is the implementation that goes with the flowchart that we saw earlier. So we set the number, calculate the number of rows, the number of columns, they just come from there, it's easy. Set start row is equal to num rows minus 1. Okay, so we're starting at the end and working backwards. Okay, so we loop over the rows in reverse order. That's really important. So we loop I from start row while I is greater than or equal to 0 minus I. So I will start at start row and then go down. We extract the current result for this row, so current result is equal to row echelon matrix dot get element at, so we get the element at I comma num cols minus 1. Okay, so that corresponds to the B term that we're dealing with. Okay, we then compute the cumulative sum as we go, so we initialize a cumulative sum variable to 0, of course, static casting to type T, and then we loop j from I plus 1 while j is less than the number of rows, and then we calculate the cumulative sum as we go. So cumulative sum plus equals to the row echelon matrix dot get element ij multiplied by output dot get element j. Okay. Now, the really important thing to note, and note that we are taking this result from output, and we've initialized output here with the values of bvect data, which would make no sense to use in the first instance. So the very first term that we're calculating corresponds to start row, which is number of rows minus 1. So for a situation where we have 3 equations and 3 unknowns that we looked at in the example, I mean start row is going to start at 2. Okay, num rows is 3, minus 1 is of course 2. Okay, so when we come back to here, we start I from start row, so I is going to be equal to 2, right? And num rows is 3, and we're looping j from I plus 1, which is of course going to be 3, while j is less than 3. Now of course j then is immediately equal to 3, 3 is not less than 3, so this condition will immediately be false, and that means in the first instance this function, this block of code here, sorry, this is not a function, this loop will not execute. Okay, so cumulative sum will remain as 0. Okay, and then we come back down here, so we come straight down to here, we get final answer is equal to current result minus cumulative sum, which in the first instance would be 0, divided by row echelon matrix dot get element at I. And then we store that into the output, that is we output dot set element I, and final answer. Okay, and then we loop through again. So the first time round, this loop here does not evaluate, so cumulative sum remains as 0, so this will work. The second time round, this loop will evaluate, but now we've already set the first element of the output to be what we want, so this will now make sense. Okay, so if you work that through on a piece of paper or go back in the video and look at the flowchart, then I think that should make sense. It should be clear. And this was the reason why in the slides I went for the slightly incorrect mathematical notation, because it best represented this. So the way we can do a loop in code, we can make sure that the loop simply doesn't evaluate in the first instance when I is equal to start row, but then it will evaluate for all of the subsequent rows or values of I after that. Okay, and that's actually it. It's quite a short function. It's only, what, there's 73 lines of code. And that is all we need to implement the Gaussian elimination method to solve a system of linear equations. Let's have a look at how we'd actually test that. So I've created a new function here called testcode_qblindsolve.cpp, and we're really just going to use this to, you see I've copied and pasted this from somewhere else. We're not dealing with the MB math library, don't worry about that. Okay, so basically we just include all our stuff. We bring in qbmatrix.h, qblindsolve, which for now I've just put in the same folder as qbmatrix and of course qbvector. And I'm using namespace std. Don't always like to do that, but I do find it quite useful when writing test code, just saves a bit of typing. And I brought in the print matrix and print vector functions that we've talked about in the previous videos where we've looked at testing our code. We don't need to talk about those. And then in our main function, simply display a bit of an introduction. The first thing we do is generate a square matrix to test things with, simply called test matrix. In fact, it's not square, is it? It's size 3 by 4. Let's correct that. We generate a matrix to test things with, so it's 3 by 4, and we print that out so we can it's what we think it should be, and we convert it to row echelon form, and then we display the row echelon form so we can see that that works. We're going to then define another matrix as the first part of a system of linear equations with the terms defined there, and that's a 3 by 3. We set that up here. Okay, and we set that up in the equations in the form of ax equals b, where a is equal to that matrix you've just defined. We then define a vector for b containing these terms here. Okay, so you'll see these correspond to the system of equations that we had before. And we define b vector there, so that gives us the value b. And then we're going to use qblindsolve there to actually compute the solution. So we just do qb vector of type double, test result is equal to qblindsolve of type double, and we pass the reference to amat that we defined here, and bvect that we defined here, and that should then give us the result. And just to show what happens if we put in, because obviously not all sets of equations will have a unique solution, so this is an example where there is no unique solution. We define the A matrix there and the B vector there, and then everything else is exactly the same, and we display the result of that. And then what I've done is, in order to make it easy to create more extensive testing, I've written some code here to do random tests. So we set up a random device to generate a distribution of real numbers from -25 to +25 in, at the moment, 10 unknowns. And we simply define a vector for our coefficient data and for the unknown data. Okay, so we're actually going to calculate use known values for the unknowns, if that makes any sense. And we're then going to calculate what the results should be, and then we use qblindsolve to calculate what the unknowns should be based on those, assuming that we didn't know them. And then we can compare the known unknowns with the values that we've computed, if that makes any sense, and we should see whether or not it works. So basically we create a random coefficient matrix, and then we create the random unknown values, and then we can actually calculate what the results of the system would be by simply multiplying the coefficient matrix by the unknown vector. Okay, unknown vector, of course, is our vector of unknown values, and that will give a system result. And then we use qblindsolve. We just pass to it the reference to coefficient matrix and the reference to system result, and that's going to give us a vector called comp solution, and then we can compute an error vector simply being the difference between unknown vector and comp solution. Ideally they should be the same, so error vector should contain all zeros. Pretty straightforward. Okay, so if we go to terminal window, we can compile this quite easily. Here we go. Let's just run that. Test code underscore qblindsolve, and if we run that, there we go. Now let's just go back to the beginning. There's quite a lot going on there. Okay, so the first thing we do, we tested conversion of a matrix into row echelon form. We started with this matrix here, and then we see that we've converted that successfully into row echelon form. We set up try solving a system of linear equations in the form ax equals b, where a is equal to that and b is equal to that. It gives the final result of 4, 1, minus 6, which is correct. And then this example should have no unique solution, so a is equal to that and b is to that, and we see we get a result here that doesn't make any sense. And if we look at the row echelon form there, the matrix of the matrix A, we see that clearly that's going to be a problem. There's no term there. Anyway, we'll come back to that later. We then generate a random coefficient matrix. I don't know if can I just rearrange that so we can see it better. There we go. So it's 10 by 10 coefficient matrix and a set of random unknown values, and we compute the equation results, and then we solve the system of equations, which gives this. And you'll notice these values are the same. So minus 12.870, which is the same as that one, 4.423 is the same as that one, 9.345 there, minus 16.163, and so on. And indeed the error vector, when we calculate the comparison of those, we see those terms are all 0. Okay, so that's really everything that I wanted to talk about today. We've had a look at the theory behind using Gaussian elimination and the method of back substitution in order to solve systems of linear equations, and then we've gone on to have a look at how we would actually implement that in C++, creating the qblindsolve function, which allows us to do that. The user can simply specify the system in terms of a matrix and a column vector, pass that into qblindsolve, and if there is a unique solution, they get the answer out. Now, as we've seen, and as we know, of course, not every system of linear equations will have a unique solution, and as it stands at the moment, the function that we've created simply gives nonsensical results if we put in coefficients that would lead to such a system. What we're going to look at in the next video is a way that we can use to detect if there's likely to be a solution before we embark on actually calculating the result. And we're going to do that by determining the rank of the matrix. Anyway, that just leaves me to say that it's been a great deal of pleasure making this video, and I really hope you've enjoyed it and found it useful. If you have, do please remember to hit that like button, and if you haven't done so already, please consider subscribing to my channel so that you don't have to miss any future videos. Well, listen, it's been a pleasure, and I really look forward to seeing you in the next video. Thank you very much for watching. Bye!